California just got hit again. Another earthquake, another sudden movement beneath a state where millions of people live every single day. For most people, an earthquake notification appears on a phone, gets a quick glance, and disappears. But there's one word in this story that changes everything. Again. Because when California shakes once, people notice. When it happens again, they start asking questions. Are these earthquakes connected? Is stress moving through the fault system? Is something changing underground? And inevitably, one question rises above all the others. Is the San Andreas fault sending a warning? Now, before we go any further, there's something important to understand. One earthquake does not mean the San Andreas is about to rupture. It doesn't mean the big one is coming tomorrow. And it doesn't give scientists a countdown to some massive event. But that doesn't mean scientists simply ignore it. They look at where the earthquake happened. They examine how deep it was. They compare it with other recent earthquakes. They study the surrounding faults. And most importantly, they watch what happens afterward. Because sometimes the earthquake itself isn't the most important part of the story. It's the pattern that follows. California is no stranger to earthquakes. The state sits along one of the most active tectonic boundaries on Earth. Deep beneath the surface, enormous pieces of Earth's crust are constantly moving relative to one another. The Pacific Plate is moving northwestward relative to the North American Plate, and that movement doesn't happen smoothly everywhere. Instead, faults can lock, slip, bend, and accumulate stress. Sometimes that stress is released in tiny movements that nobody notices, and sometimes it produces earthquakes that people can feel. And sometimes, when enough stress is released across a large enough section of a fault, the result can be devastating. That's the geological reality of California. But there's a detail that often gets lost whenever an earthquake makes the news. The San Andreas isn't the only fault in California. There are numerous active faults spread throughout the state. Some are famous, some are barely known outside the scientific community. And an earthquake somewhere in California doesn't automatically mean the San Andreas caused it. That's why scientists begin with a much simpler question. Where exactly did the earthquake happen? Because that single detail can completely change the story. When an earthquake occurs, most people immediately look at one number, the magnitude. Maybe it's a 3, maybe a 4, maybe a 5. And it's tempting to assume that the bigger the number, the more important the earthquake must be. But earthquake science isn't that simple. Magnitude tells us about the size of the earthquake. It doesn't tell us exactly how strongly every person experienced it. Depth matters, distance matters, local geology matters, and population density matters. Imagine two earthquakes with nearly identical magnitudes. One happens deep underground in a remote region. The other occurs much closer to the surface near a heavily populated area. The effects can be completely different. That's why scientists don't stop at the magnitude. They ask where the earthquake occurred. How deep was it? What kind of movement produced it? Was it near a known fault? Were there earthquakes before it? Were there earthquakes afterward? And is the activity unusual for that region? An earthquake isn't just a number, it's a piece of information inside a much larger geological system. And that's where the San Andreas enters the story. The San Andreas Fault is one of the most famous geological features in the world. It stretches for roughly 800 miles through California and forms part of the boundary between the Pacific and North American plates. But despite how often we hear about it, the San Andreas isn't one simple crack running perfectly through the state. It's a complex fault system. Different sections behave differently. Some areas have experienced major earthquakes in the past. Some portions can slowly creep. Other sections can remain locked for long periods while stress accumulates. And this is one of the reasons earthquakes are so difficult to predict. You can't simply look at a quiet section of the fault and say nothing is happening, but you also can't look at one earthquake and immediately declare that a major rupture is coming. Both conclusions would be too simple. The Earth doesn't work that way. The crust is constantly moving. Stress is constantly being redistributed. And scientists are constantly trying to understand those changes using instruments capable of detecting movements far too small for humans to feel. Which brings us to one of the biggest questions surrounding every new earthquake. Can one earthquake predict another? Imagine an earthquake happens today. Then another one occurs nearby tomorrow. Then another appears. Our brains immediately want to connect the dots. 1, 2, 3, something must be happening. And sometimes earthquakes really are connected. They can occur as part of aftershock sequences. They can form earthquake swarms. They can cluster around particular fault structures. But sometimes earthquakes are unrelated. That's why scientists cannot simply look at one event and say, a major earthquake is coming. There's no reliable countdown clock that turns one earthquake into a guaranteed prediction. Instead, researchers examine probabilities and patterns. They study seismic sequences. They analyze historical earthquakes. They measure tiny movements of the Earth's surface. They examine how faults have behaved in the past. And they compare current activity with the normal background activity of a region. An earthquake can be a clue, but a clue is not a prediction. And that distinction matters enormously. Because now we come back to the most interesting word in the title, again. What does again actually mean? When people hear that California was hit again, they naturally imagine a connected sequence, one earthquake, then another, then another. But scientists have to ask a much harder question. Are these earthquakes actually connected? How far apart are they? How much time passed between them? Did they occur at similar depths? Are they located along the same fault structure? Are they part of an aftershock sequence? Or are they simply separate earthquakes happening in a state where earthquakes are already common? Those questions matter, because two earthquakes can look connected on a social media map while having completely different geological causes. That's why scientists don't just count earthquakes. They map them. They examine their depths. They calculate their locations. They compare them with known faults. And they study how the sequence changes over time. One earthquake is a dot. Several earthquakes create a pattern. And sometimes the pattern is far more informative than the individual event. Imagine opening an earthquake map of California. At first, there's one dot, then another appears, then another. Now imagine all three earthquakes occurring hundreds of miles apart. That tells scientists something very different from three earthquakes clustered tightly around the same fault. Now imagine the earthquakes forming a line. Researchers can compare that line with the geometry of a known fault, or imagine the earthquakes becoming progressively shallower. That could raise another set of questions. Or imagine seismic activity suddenly becoming much more frequent in one small region. Again, scientists pay attention, not because any one of these patterns automatically means a major earthquake is about to happen, but because unusual patterns can tell scientists where to look more closely. That's the difference between watching for signs and claiming to know the future. Scientists aren't necessarily saying, we know what's coming. They're saying, something happened here, let's understand it. And that's a much more scientifically honest way to look at earthquakes. So is the San Andreas actually sending a warning? This is where we need to separate the dramatic language of a headline from what earthquake data can really tell us. An earthquake somewhere in California isn't automatically a warning from the San Andreas. If the event happened on another fault, then it would be misleading to pretend that the San Andreas itself produced it. But there's another meaning behind the word warning. Every earthquake is a reminder that California's tectonic system is still active. The plates are still moving, faults are still interacting, an earthquake risk hasn't disappeared. That's not a prediction. It's simply geology. California doesn't suddenly become safe because there hasn't been a major earthquake recently. And it doesn't suddenly become certain that a major earthquake is coming because another moderate earthquake happened today. The bigger story is the long-term hazard, and California's history makes that impossible to ignore. California has experienced major earthquakes throughout its history. The San Andreas has ruptured before. Other faults have produced destructive earthquakes as well, and some major earthquakes have happened after long periods when the surface appeared completely calm. That's one of the most deceptive things about earthquakes. Quiet doesn't necessarily mean inactive. A fault can remain locked while tectonic plates continue trying to move. Stress can accumulate for years, for decades, sometimes much longer. But here's the problem. Scientists can't simply measure that stress and turn it into an exact date. Earth's crust is too complicated. Faults interact with one another. Rock properties vary, stress can move through the crust, and the precise conditions that cause a fault to rupture aren't simple enough to predict like tomorrow's weather. So California's earthquake history doesn't tell us the next major earthquake is coming now. It tells us something more useful. The possibility is real, and that's why scientists continue watching even when everything appears quiet. Today, California has an enormous network of technology monitoring its movement. Seismometers detect earthquakes and help scientists determine where they happened and how they behaved. GPS stations can detect tiny movements of Earth's surface. These movements are often far too small for people to notice. Satellites provide another perspective. Radar-based techniques such as INSAR can reveal subtle changes in the shape and elevation of the ground. Researchers also study the faults themselves. They examine rocks. They analyze historical earthquake records. They investigate previous ruptures. They compare today's activity with older seismic sequences. Each system provides another piece of information. But there's something important to remember. No single instrument can predict the next major earthquake. A seismometer doesn't know the future. A GPS station doesn't know the future. A satellite image doesn't know the future. Scientists combine these sources of information to build a better understanding of what the Earth's crust is doing. And after an earthquake, that monitoring doesn't stop. In many ways, it becomes even more important, because scientists want to know what happens next. So what would actually make scientists pay closer attention? Not necessarily one earthquake, but a meaningful change in the behavior of the system. For example, scientists could watch for an unusual increase in earthquake activity. They could examine whether earthquakes are becoming concentrated around a particular fault. They could look at changes in depth. They could monitor whether the distribution of earthquakes is changing. They could examine ground deformation. And they could compare everything with the region's normal background activity. If several independent signals begin changing at the same time, that could become much more interesting. But even then, there's an important limit. Increased scientific attention does not equal an exact prediction. Scientists might conclude that an area deserves closer monitoring. They might reassess the probability of future earthquakes. They might investigate whether stress has changed around nearby faults, but that still doesn't tell them exactly when a major earthquake will happen. And that brings us to another question people immediately ask. Could this earthquake trigger something bigger? This is where the concept of stress transfer becomes important. When an earthquake occurs, the stress distribution around the fault can change. In some situations, that change can increase stress on nearby portions of the crust. But how much the stress changes depends on many factors. The earthquake's size matters. Its location matters. The geometry of the fault matters. The distance between faults matters. And the surrounding geological structures matter. So yes, scientists can study whether an earthquake changed stress in nearby areas, but that doesn't mean small earthquake equals big earthquake next. That's not how the system works. Sometimes earthquake sequences grow. Sometimes they fade. Sometimes aftershocks follow. Sometimes nothing significant happens afterward. And sometimes an event that initially attracts attention turns out to be relatively isolated. That's why scientists watch the sequence instead of jumping to a conclusion. Because the earthquake may be over, but the scientific investigation has only just begun. After a significant earthquake, scientists watch for what comes next. Are additional earthquakes occurring? How frequently? Where are they happening? Are they becoming less frequent? Are they remaining in the same area? Do they follow the expected behavior of an aftershock sequence? Or does something about the activity look unusual? These questions can help scientists understand what happened underground, and this is why the next few hours and days can matter. Not because scientists have a secret countdown running somewhere, but because earthquakes leave information behind. Every event adds another measurement, another data point, another opportunity to understand how faults behave. The sequence may eventually fade into the background, or it may reveal something worth studying more closely. Either way, scientists learn from it. And that is the real value of earthquake monitoring. Not predicting every earthquake, but understanding the system better. So what does this latest earthquake actually mean? After removing the dramatic language, the answer is relatively simple. California experienced another earthquake. Its significance depends on the details. Where did it happen? How large was it? How deep was it? Which fault or geological structure was involved? Were there other earthquakes nearby? And did anything unusual happen afterward? Those are the questions that matter. What it does not tell us by itself is that the San Andreas is about to rupture. It doesn't prove that the big one is imminent. It doesn't provide a countdown, and it doesn't guarantee that another earthquake is coming. But it does reinforce a fact that has been true for thousands of years. California is earthquake country. The faults are still there. The plates are still moving. And the geological system remains active. That's the real warning. Not that disaster is guaranteed, but that the risk never completely disappears. Now, the earthquake has happened. The headline has been published. The alerts have gone out. People have talked about it. And eventually, most of the public will move on. But scientists won't simply close the file. They'll keep watching. They'll monitor the seismic sequence. They'll examine new earthquake locations. They'll compare the activity with previous events. They'll look for patterns. And they'll wait to see whether the system returns to normal background activity. Because sometimes an earthquake is exactly what it appears to be. Just an earthquake. But sometimes understanding its significance requires something we don't have immediately. Time. Time to see what happens afterward. Time to compare the data. Time to understand the pattern. And that may be the most important lesson from California's latest earthquake. The real danger isn't knowing that every earthquake means something catastrophic. It doesn't. The danger is going to the opposite extreme and assuming that because an earthquake was small, isolated, or quickly forgotten, the larger earthquake hazard doesn't matter. It does. California's faults are part of a system that has been moving for millions of years. The San Andreas has moved before. It will move again. Scientists know that. What they don't know is the exact moment when every future earthquake will happen. And that's why preparation is more useful than panic. You don't need to believe that the big one is coming tomorrow. You don't need to treat every earthquake as a prediction. You simply need to understand that the hazard exists, and that scientists are watching for the clues that can help us understand it. So let's return one final time to that word. Again. California got hit again. But the important question isn't simply how many earthquakes have happened. It's whether those earthquakes form a meaningful pattern. Are they connected? Are they occurring along the same structures? Is activity increasing? Is the depth changing? Is the ground moving in an unusual way? Or will this event simply fade into California's enormous catalog of earthquakes? Right now, that's what scientists have to determine. And that's why the story doesn't end with the earthquake itself. It continues with the data that comes afterward, the maps, the measurements, the aftershocks, the patterns, the changes. and the things that don't change, because sometimes an earthquake is just an earthquake, and sometimes the only way to know the difference is to watch what happens next. California has been shaking for thousands of years. The San Andreas has moved before. It will move again. The question isn't whether the ground will move again. It will. The real question is what the next movement will tell us, because the biggest warning isn't always the biggest earthquake. Sometimes it's the pattern that comes after it. If you found this breakdown useful, subscribe to the channel and turn on notifications, because we'll keep tracking the earthquakes, fault activity, and geological changes that could tell us more about what's happening beneath California. Stay informed, stay prepared, and keep watching the ground beneath the headlines.